This video explains the design of reinforced concrete beam. Need to find the ultimate moment capacity using the first principle for 600 depth by 300 millimeter width for singly reinforced rectangular section, which is shown here. Concrete compressive strength is given 25 megapascals. To calculate the area of the stills, we have a 3 and 24 bar and 40 millimeter cover to R10 fitments. So for that fitments, we have providing the 40 millimeter covers. The fitments is to hold this reinforcement in the position, and the fitments look like this one. Now to solve this one, so we're going to use the clause 8.1.3 in AS 3600 to 810 on page number 110. Now I draw this stress block, the beam cross section here, which has a 3 millimeter by 600 millimeters. It has a 3 reinforcing bar, and it is N24. Now 538 millimeter, the way I calculated that D value is 600 millimeters minus 40. That 40 is that cover that we have it outside of this to protect this reinforced bars. So that is take away 40. So that's 40. Take away 10 millimeter is the fitment. So we have this 10 millimeters fitment. So we take away 10 millimeters from here, and then minus 24 divided by 2, because we are measuring this 530 from top to the middle of the reinforcing bar. So we have it 524 divided by 2. So that is a diameter of 24 millimeters. That's we dividing. So that will give us 538. So what we done, we minus cover, we minus the diameter of the fitments, and we just half the diameter of the reinforcement to get this 538. Now in previous video I drew the strain distribution for these sections. Now this is linear strain distributions. The concrete is in compressions. Now we are doing sagging. So for examples, the beam is rectangular beam is this, and we are compressing in the sagging moment. So in that case, we have a compression on the top, tension in the bottom. So for this compression strain, we have a 0.003 that is coming from the Australian standards, page number 110. And if you read here on clause 8.1.3, the maximum strain in the extreme compression fiber is 0.03. That's given here. The strain epsilon strain in the steel is given here. Now we already discussed about this equivalent stresses, that alpha to FC is the stress, and the depth is the lambda dn. So we will now going to find alpha 2 and lambda value here. Now dn is nothing but is just a value of ku times depth. Okay, let me get that corrected. So this dn value is nothing but that is ku times d, and d is the depth of the sections, which is 600 millimeters. So this dn is represent kud. And then we have a force that you can multiply by area to calculate the force, and the moment is the lever arm. I'm going to discuss this lever arm now. Lever arm is nothing but the distance between two forces acting, compression force and tensile force. The position of this compression force, it's going to act in the middle of this one. So if you have lambda dn, we are just dividing by 2 to see the center of that stress, that is the force, and similarly it's acting in the middle of this one, that is a tensile force. Now these d calculations we already discussed. Now we are going to divide the whole problem into the 3 sections. First we calculate the stress in the concrete, let's say force in the concrete, we calculate the force in the steel, and we then calculate the moment. So let's calculate the force in the concrete. In previous video we discussed that force in the concrete is equal to stress times area. Now that stress is alpha to FC dash, that we see here, alpha to FC dash, and area is gamma dnb. So that is gamma dn, that is the depth times this b, that's the area. So to calculate the area, Australian standards clause 8.1.3b given this note that has saying that age of the cross sections, the uniform cross section area of alpha to x on the area bounded by age of the cross sections, meaning this one, and then the line parallel to neutral axis under loading concern and located at distance of lambda gamma ku dn from the extreme compression fiber. So that is line parallel to the neutral axis, and that is the value of gamma ku d, and ku d I write here dn. Now once you have this area, we need to calculate this alpha 2 value. Now the alpha 2 value can be calculated using the Australian standard 3600.282018, page number 110. So if you go here, they have an equation to calculate alpha 2, 0.85 take away 0.015 fc dash, and please note alpha 2 value should be greater than 0.67. if you use this equation and get the alpha 2 value less than 0.67, we need to use 0.67. So alpha 2 0.85 take away 0.0015 fc dash, 0.85 take away 0.015 times fc 25, that is given in the questions, is a concrete compressive strength, fc given 25 megapascals. So we substitute 25, we get 0.18125. Now this gamma value is 0.97 take away 0.025 fc dash, and that gamma value has an equations coming from page number 110 on clause 8.1.3. gamma is equal to 0.97 take away 0.025 fc, and that gamma value would be greater than 0.97. So once you substitute this fc value 25, that is given in the questions, again this fc value is 25, we substitute this value, we get 0.9075. now once you have this alpha 2 and gamma value, we can substitute the value. Alpha 2 0.8125, that we just calculate, fc dash is 25, that is coming from the questions, fc dash is 25 megapascals, times gamma 0.9075, we just calculated. dn we don't know, dn is nothing but depth of the neutral axis, so that is the dn. From the top of the concrete to the middle, where you have a difference between the concrete, and when the zone are differentiate between concrete and tensions, there is a neutral axis, that distance dn we need to calculate, we don't know. So that dn is we need to calculate. Width b is given in the questions 300, and that is 300 given in the questions, we also use it here, and that multiplication give 5530 dn. So this is the first steps, we calculate the stress in the concrete in terms of dn, we don't know dn. Now the steel calculation is relatively easy. Steel stresses in the steels, please note this one as a compression stress or compression force in the concrete, and now we are dealing with tension force in the steel. Now there is a one condition that we need to always look for, that always steel is in the yielding, we assume that. What is that meaning? That if you have a reinforced concrete, we like to fill the steel first, then the concrete, so concrete should be filled after the steel. So if someone asks the questions, if you have a reinforced concrete, which component is failing first, is it concrete or steel? So we are saying that steel is fail first and then concrete fails, so steel is yield. So we have a steel should be yielding, we can't use this equation if the steel don't reach the yielding point. So if I take an example here and explain in the more details, that for examples, if I draw the stress strain curve for steel and concrete, in that case we have a, let's say, strain and stress. If I draw the concrete one here and then the steel one here, in that case where this yield point of the steel should reach first, then this reaching this point, so this is correct. So this is the yield strength, and let's say this is the ultimate strength, yield strength, so that is correct. Always yield strength is less than the concrete ultimate strength to make sure that it's yielding. And then if it is this condition is correct, then we have a tension equal to yield strength times the area of the steel. Now we have we have given n 24 bars. It has a 500 megapascal yield strength. If it is not given, you can take it from our Rio data guide and area of the steel. So 500 megapascals times 1356. So we have a document here that will give us the detail about this this Rio data. And if you flip some of the page, if you flip some of the page, you will see that if you are using the 24 bars and it has a number of 1356 millimeter square is the area. So that is 1356 millimeter is the area. I also use that 1356 millimeter here area. So multiplication gives this number 67800 newtons. Once you find the area, which is the area of the steel bars 1356 as from the Rio data, we know that this cross sections is in equilibrium. What does it mean? Whatever the compression acting here should be equal to the tension acting at this end. So they are in the equilibrium. So sum of the force in the compression equal to sum of the force in tensions. So we know that compression is in the concrete, and we calculate 5530 dn. We just calculate 5530 dn value, and then we calculate the tension 67800 force, tension force in the steel. If you equate that, you can find dn by dividing 5530 by this big number. So that will give us 122.6 millimeters. And we can calculate gamma dn is equal to 0.9075. We calculated gamma value in the previous step, 0.9075 times by 122.6 give us 111.3. Now we have assumption saying that still tensile steel should be yielded. So for this case, for this dn value, we making sure that it should be yielded. So I just draw the strain diagram again, and this is the depth 122.6, that is the depth that we calculated. Now this region here, which is the, let's say this is compression and tension, this tension region we calculate 538 millimeters. If you remember that one, in this one 538 millimeters that we calculated, minus 122.6 is give us 415.4 millimeters. So that distance is 440. So if you use similar triangle concept, this strain divided by this distance equal to the strain that we have EAST. For example, this one here is the EAST. Then EAST divided by 415.4, then EAST can be get 0.01. Now we need to calculate yield strain of the strain. ESY is the stress over Young modulus, and we know the stress is 500 megapascals and the Young modulus of the steel is 200,000 megapascals. So that gives us 0.0025. So comparison gives that this value is bigger than the yield strength. So definitely that will yield. So lever arm, we need to calculate lever arm. What is lever arm? Lever arm is nothing but that is the distance between the compression of this force and the tension force. Now please note, this compression force is acting in at the center of this area. So if this depth is lambda gamma dn, then it should be acting from the top. It should be half of gamma dn. So it's acting in the middle of this one. So if you want to calculate the lever arm, then we know that this depth is d 538. So that is the up to here. So that is 538. Take away this distance will give us z, because we know this is 538. Take away this distance will give us z value. So that's what I done. 538 take away half of gamma dn, and gamma dn we just calculate 11.3. So that's lever arm give us 482.35. so that's lever arm distance is 482.35. so ultimate moment is nothing but you can get the tension force times the z value, or you can also calculate the compression force times z value. Both will give you the same answers. Here simplest things, we already know the tension value, tension force value, which is we calculated 67800, times by 482.35. That's we just calculate lever arm, that give us 327 kilonewton meter. So that is the answer. Thank you.